Good afternoon, everyone. So it's a pleasure to have Professor Stephanie Telex with us today. So Stephanie is an associate professor at Brown University, and she's also been spending some time at the Boston Dynamics AI Institute. Stephanie has done some awesome work during her journey. Um, you know, Ranging from how humans and robots can work together, what is the role of language, how to learn skills, how to compose skills, so on and so forth. Her work has been widely decorated and awarded with multiple honors. For example, the NSF Early Career Award, the NASA Award, one of the breakthrough technologies from MIT Tech Review, and the list is very long. The one thing, today we were talking about is that many people in robotics, talk about how to generalize to new skills, but still, having one skill and making it very robust seems quite far. And I find that very exciting. And, a lot of us, have seen what robots can do with language in the era of LLMs, but Stephanie has been on that boat a decade before. So, it's a pleasure to have Stephanie come here, and welcome back to MIT. And, please take it away.
Thanks for the lovely introduction. One of the most rewarding things about being a professor is your students, and it's been really fun today to hang out with Rachel, Seiji, Aaron, Nishant, who are all undergrads in my lab and have come on to have awesome times here with y'all at MIT. That's no joke, that's the best reward of all, to hang out with them and see them do great things. So I'm at Brown, and this talk is mostly going to be about Brown stuff, but I was at real time, and I still have stock, so let's hope that good things happen to them. And I am currently, since January, 80% at the AI Institute on leave from Brown, 20% at Brown, leading a team with Rob Platt, who I think was here a few weeks ago, thinking about manipulation, planning, and learning. It's been a lot of fun. But most of what I'll talk about today is Brown stuff. But I'm happy to take questions about anything. Talk to me about anything. So Skydio used to be my favorite robot. I do think they're awesome. I love them. But my current favorite robot is Spot. Sorry, Adam, Dave. We've seen amazing progress with these quadrupeds. When we first got them, I thought we were going to have them be falling over all the time, and they would be kind of showpieces that would not move very much. But actually, they're super reliable and super robust, and we've been able to do a whole lot of really awesome stuff with them. One of my favorite things to do is dancing. Got the music. This is my student Ifra, hey Luca, who's at Amazon Robotics, or Amazon Astro team over in Seattle, Bay Area.
I feel so far from where I've been. I got my eggs and my pancakes too. Got the maple syrup, everything but you. I break the yolks and make a smiley face. I kinda like it in my brand new place. I wipe the spots up over me, don't leave the keys in the door. I never put towels on the floor anymore, 'cause dreams last for so long. Even after you're gone, I know you love me, and soon you will see you were meant for me, and I was meant for you. I called my mom.
So my students are amazingly talented. Like, I don't know, like this is just, like the stuff that they come up with is really cool and really awesome. We've had more than one student make dances like this. And what's interesting is, like, this is one of the most state-of-the-art robots in the world, and doing one of the most state-of-the-art things, which is like, dancing and stuff. And so I was really interested to learn about the interface that you use to tell it what to do. So this is the tablet interface for Spot, and Leslie has one in her lab, and I'm sure she'll let you drive it. You can ask Seiji if he'll supervise. You don't speak for that spot. Okay, well, if you, in my own behalf, I invite you to come visit the AI Institute, and I will definitely let you drive it there. It's this fairly complicated and involved interface. It's letting you control the robot, letting you make it move around, letting you control both the base as well as the arm and the end effector in order to do things both at the low level and at the high level. The dance interface, this is the choreographer interface that they shared with us. This is what they're using to make, BD is using to make all of their dances. It's basically like Scratch. If you have kids, they all know Scratch now, like this block-based programming thing where you're dragging these dance moves into the thing and telling the robot what to do at a fairly low level of abstraction. And so even with one of the most advanced robots in the world today, the primary way that we're interacting with it is through these kinds of interfaces where we're telling the robot what to do at a fairly low level. And you have to be fairly technical to make this happen, to do this. So instead, what my lab is trying to think about is, and what we've been thinking about, as Pulkit was saying, for a long time, before LLMs kind of took off and everything, is how can we make a robot interact with a person using language? And so, for example, instead of using an interface to program the robot to look around, you might want to say to it in words something like, find the mugs in the library or the living room or the kitchen, and have the robot take that information from language and take information from its sensors and then plan actions for where to go in the environment and figure out what to do. And believe it or not, I still think this is an important problem, even with GPT-4. And it's still an unsolved problem, even with the tremendous progress we've been seeing with LLMs. And I'll talk a little bit about that today in this talk. I think there's a lot of aspects of this that aren't addressed by existing work in robotics. And so I'll talk a little bit about that, both in the sense of like partial observability, so trying to think about what to do when you're trying to understand language and you don't have a complete model of the environment, or the language is telling you things and you want to fuse the things that it's telling you with your partial model of the environment. Fundamentally, the challenge of language and robotics is that people want to talk to robots about everything they see and everything they do. Everything. And so that means the language system needs to connect to every single other part of the robotic system if you really want to understand language, in writ large. And nobody knows how to do that today. That is still very much an unsolved problem. It's really easy to come up with natural language commands that are talking to the robot about stuff that's at the wrong level of abstraction, or you haven't hooked that part up yet, or there's just no way that this could be in the LLM, or it's not in the sensor or something. To make this cross-cutting thing. And yet, that's what language is for. When would you use language versus some other interface, right? Rod Brooks, if you've ever heard him talk about iRobot and the Roomba, he talks about the interface for the Roomba. They had all these buttons for what you wanted the robot to do, but eventually they realized that the Roomba only needed one button, clean, right? Just the one button. And that was the right interface for the Roomba. When you have a predefined set of things, the interfaces like the dancing interface and stuff are great. Like they do what their job is. But when you really have problems where the robot's behaving highly autonomously, doing lots of things, chaining long things together, where you really want to talk to the robot about everything, it gets really hard to stuff all that into a tablet interface or a keyboard and mouse GUI or a programming language where you have to remember stuff when you're typing to the robot. You really just want to be able to talk to it as if you're talking to a person. So I'm going to narrow this down into a couple different subproblems because we can't work on them all. And the first subproblem I'm going to think about is object search. And we got interested in this problem because I really wanted to make the robot be able to find objects that the person was talking about. It seemed like the most fundamental thing is like, I'm talking about something and I want you to find it in the environment. Maybe I want to pick it up and give it to you. Maybe I just want to know where it is. Maybe I want to tell you, answer a question about it. Maybe I want to manipulate it, like open a door or a drawer. But the first thing is to find the object. And I think this relates to one of the superpowers of robots compared to the data sets. We usually work on in computer vision. Most of the data sets in computer vision are this, right? Like we're collecting images and video from a person, pointing the camera, and clicking record. Whereas a robot has its own camera, and it can decide where to point the camera in the environment. It's in the environment right now today when it's running, and it can walk closer, it can walk farther, it can move behind occluded objects and figure out where things are. And so I wanted to think about like how can we move the camera in an effective way to just start out by trying to find an object. So in our first pass at this problem, we formalized this as a 2D grid map. We thought about it like SLAM, like you ran SLAM and you have a map of the environment and you're localizing yourself in the map. And then you're getting some information about where the object is from language. So here they're giving some rooms. And it's a semantic map, so pretend we have Luca to help us make a semantic map of the environment, although this is only 2D. And label it with these rooms. And then given the information from language, you can have a prior distribution on where you think the object is. So the red dot is where the robot is in this picture. And then the blue is like a probability map. And the lighter it is, the more likely it is the object is in that location. So you just do some Bayes stuff, and you get lighter in the grid cells that are in the library, living room, and kitchen. But then you're a robot, and you have a camera, and the camera can move. So we assume that you're equipped with a sensor that can look at the environment and detect the object. But it's not a perfect sensor. It's got a limited field of view, a limited range, and a noise model. And so we can put that into a model, and we define this as a POMDP, partially observable Markov decision process, with an observation model, a transition model, and stuff. And then you can solve the POMDP to find a policy. And what you hope happens is that the robot drives into one of the rooms and then points its sensor somewhere and then looks. And then after it looks, it doesn't update. So in this case, it doesn't see the object. So those grid cells get dark because it didn't detect anything. So then it turns and it looks again. And now it does detect the object. And so now it's happy and knows where the object is. So this is what you want to have happen. The challenge is if you write this down as a POMDP, POMDPs are big and hard and challenging to solve. And so if you write it down as a POMDP and try to solve it naively, we can't, even though the optimal behavior is this, if you did solve it, you're not able to efficiently find this optimal policy and get the robot to systematically search the environment, taking into account information from its sensors as well as information from language. So to make this happen, we had to make a new kind of POMDP, which we called object-oriented POMDPs, where we're factoring the state of the POMDP according to the objects, assuming the locations of objects are independent of the locations of other objects. And then this gave us a new inference algorithm, object-oriented POMCP, which was an extension of the original algorithm, which was POMCP, partially observable Markov chain. I forgot what the P is. And that lets us get this behavior very quick with very quick inference times. So we did a whole bunch of experiments of this in simulation. But my favorite one is this one. So I'll dig in on this one. So here what we're showing on the y-axis is the reward. So you get a small cost for being alive for every step that you take in the environment, and a large positive reward for finding the object. And what we're changing on the x-axis is the amount of information we're giving in language. So in the misinformed case, we're lying to the robot. We say, robot, it's in the kitchen, but really it's not in the kitchen, it's in a different room. In the uninformed case, no information, we don't say anything. We don't lie, but we also don't give it any positive information. In the ambiguous case, we say it's in the kitchen or the living room, and we're right. It's in one of those two rooms, but we don't tell it which room. So we're helping it, but we're not giving it unambiguous information. And in the informed case, we say it's in the kitchen, and it actually is in the kitchen. It still has to go look in the kitchen and find it, but we're not lying to it. And then the two baselines I'm showing right now, on the bottom is the performance of a random algorithm, where we just drive around the environment randomly. And at the top, it's the cheating baseline. It's an oracle, where we just show you the reward if you drive straight to the object by the shortest path. So it gives you, like, you don't have to find the object. There's not actual search going on for the upper bound baseline. So this magenta line is the performance of POMCP, which is the previous state-of-the-art algorithm. So we're doing better than random, but not very close to the Oracle. There's a lot of random actions it's having to take. And then these lines are different variations of our algorithm, which is object-oriented POMCP. And what you get to see is this beautiful pattern where in the misinformed case, we don't do that. It gets less reward because we lied to the robot. So the robot has to go to the room that it believes you, basically. It goes to the wrong room, searches there first, and then doesn't find it. There's some smoothing, and then it goes to all the other rooms and searches until it finds the object. That's not as good as the no information case, and that's not as good as the ambiguous case. And the informed case is almost but not quite as good as the Oracle, where we drive straight to the object, because we still have to search in the kitchen in order to find the object. And if you're like a Bayesian POMDP kind of person, the fact that it's doing this isn't surprising. This is what the Bayesian math you would like it to do. Like, this is why you paid the cost of doing all this Bayesian stuff. But what's cool is that we're able to do it quickly and efficiently and find these policies in realistically sized environments. So this was all done in simulation. In a grid world, we also made it work on a real robot. We have a MOVO. I saw you guys, Leslie's lab has a MOVO. Who was showing me Leslie's MOVO? You, Seiji. Wasn't it you? Might have been Sam. So we also have a MOVO, and this is the MOVO driving around in different environments, looking with its camera in order to find the object. And in this work on the real robot, we were using April tags for the detector. But of course, it's agnostic to what the detector is, right? So in this case, it's an April tag detector thing that we were running on the robot's camera. But in follow-on work, and of course, large language models and vision and language models came, it's very natural to use that as a detector. So you can take a VLM, define, learn, or make up an observation model for it, and then it will run on spot, and you can have the robot automatically decide where to point its camera, where to move in the environment for arbitrary language descriptions. So in this case, the green mug on the left, and then the robot automatically decides where to go in the environment in order to find objects. So you can plop in and out whatever detector you want, wherever it might come from. In follow-on work, we've also extended this to 3D. So my student Kai-Yu Zhang had an IROS paper. It won RoboCup Best Paper last year. So when you extend object search to 3D, so think about a drone or a MOVO camera with pan tilt and in the base that can go up and down, or an iron-hand camera that can point in any old direction. Then you have to think about the 3D voxel grid and probability maps in the 3D space. So the problem gets much larger, and you have to play more tricks. In particular, the trick that we played was exploiting hierarchical abstractions with octrees in order to efficiently find policies to point the camera in 3D spaces with occlusion. And we made this run. This is showing the video of it deciding where to go in order to find the object, the detection running. And we made this run on the MOVO robot as well as on our Spot robot. And it could do things like find a cat, a stuffed cat, because it was a lab, but like find a cat under a couch, because it can move up and down and go behind objects and stuff. And Kai-Yu's now at the AI Institute working on doing this in that setting. Okay. So this is object search. And I think what I liked about this work, and I still like about it, is it really takes seriously the idea of moving the camera around and thinking about where to point your camera. I think we in robotics, all of us, me included, need to do more of that. I think that's a superpower that we've only just begun figuring out how to leverage. And lots of what language is for in humans is telling you stuff like that. You know, when you say the mug is on the table, you're not telling the person which mug of all the mugs that you're talking about, the one that's on the table. You're telling the person where to look. The table's big and easy to find. And I can more easily find the table and then look on the table. You're giving a search strategy for something like object search. Questions for that part of the talk? We're going to switch gears and talk about language. Yes.
What if there's like a misalignment with, maybe the human wasn't lying, but they were wrong?
Yeah.
Have you thought at all about how you might communicate that back to the human? Like some misalignment between what was assumed to be common ground?
Yeah, I'm not going to talk about it in this talk, but my student Ifra, the one who was dancing at the beginning of the talk, has done some work with dialogue and noisy sensors trying to watch the person doing tasks and then actively ask questions in order to narrow down on the uncertainty. There's a lot of work in the dialogue community about POMDPs for dialogue. That's one of the success stories for POMDPs is being used in that setting. So I would really love to try to figure out the right way to have that back and forth dialogue. The challenge with dialogue is that you can have a data set for it, but it's not about the data set. It's so easy to go off the path of the data set because you want to be able to, the whole point of it is I can dynamically ask a question, and that a question I want to ask now probably wasn't the one that was in my data set. And so it's been very challenging, I think, for people to figure out how to do that in a way that transcends the data set. And some of the work in the dialogue community that's used deep learning to do dialogue state estimation had this flow where they would generate dialogues with a generative model, or they would have like at CMU they would have a bus answering system, a bus scheduling system, and people would call up the system and talk to it, and talk to essentially a crappy generative model, which would then create a data set, which they would then use to learn a discriminative model, which they would then put back on the real system, and it would work better than the generative model did. But it still doesn't transcend the data from the generative model. You're kind of limited to the data that you have. And I don't really know how to get out of that. But we've been poking at dialogue in various ways. I think that's what you're kind of asking, how can I get into a dialogue with the person? I do think this kind of probabilistic lends itself to that because I'm thinking about the uncertainty and I'm thinking about different things I can ask about. And I'm fusing information multimodally from different sources. Yeah, thanks. Any more? Yeah. Can it handle unknown objects? So in some sense, that's what it's about. The detector, so when I go back to the green mug on the left, I don't know if you think that counts as an unknown object, but there's no detector or anything. It's just a vision and language model that's been trained on the internet, to become a detector for the green mug on the left. So in the sense that the VLM has to have seen something that it's able to recognize, it's not an unknown object. But in the sense that now that we have vision and language models trained on the internet, there are very, very, very few unknown objects left, whatever that even means. Maybe it doesn't, but I don't know if it matters. And it also is completely agnostic to the detector. So we can plug in, if you make a better detector, we can just put it in and it'll work. It can go from April tags to VLMs and it's fine. Yes?
Just curiosity, I was thinking when I saw this slide, was this the real input? The green mug on the left?
Yeah.
Because it's on the right.
Ignores it. There's no information in the VLM about, well, it might be on left and right. So that's another question in terms of unsolved problems with GPTs and stuff. Spatial language like left and right and front of and behind. So I totally believe that if you showed it an image of the green mug, and it would decide probably it's the image frame or our frame looking at it. It's on our left, but Spot's right. When you use these spatial language expressions, you say, you're implicitly talking about a posterior that you're imposing in some 3D space, I think, with some frame of reference, right? So part of what's going on here is the frame of, when I say left, you're saying, well, it's not the robot's left, but it is our left, the camera's left and right? So there's some frame of reference that's being placed implicitly. And Caillou had a paper where we did that. So we did this in OpenStreetMap. I don't have slides for it, but we had models for left and right and front and behind. We annotated a data set of the frame of reference for a whole bunch of spatial commands. And then we said the green mug on the left, it was like the car behind the building, but like the same deal. And it actually did use that information. So using the model, it would ground the building with the building in the map, and then it would update the probability to be like behind the building, and then it would go behind the building and look for the car. But it was ugly, the way that we had to annotate the frame of reference and really encode the space that it was searching. And I think that's still a really interesting open question. In this particular, I don't have a video, but this was a video, that it ignored it. It's whatever the VLM made of that, and each individual image is what it did. Yeah?
What if you just said, like, the thing on the table, and there was nothing else on the table?
It's whatever the VLM will do, right? So if the VLM can handle that, then it would work. And if the VLM can't handle that, then it won't work. Caillou had another paper where he was, if you said find the sponge, sponges are small, and so they're implicitly hard to see because they're little. If you're just standing in the kitchen looking, something like the refrigerator is much bigger and more distinctive than the sponge, which is small. So he assumed that he had access to data sets of correlations between objects, as well as models of how hard it was to detect various objects. And then he could decide if it's looking for the sponge, that's correlated with refrigerators because they're both in kitchens. And so find the refrigerator first, and then once you find the refrigerator, look around there for the sponge. Whereas if it's like a couch, you can just look for the couch because it's big, and you don't need to do this step of looking for something else first. I think there's a lot of really interesting work extending that idea. Yeah, but at the level I've taught, what I put in the slide so far is just whatever the VLM does. It's agnostic to the detector. It's not about the detector. Yes? How do you know when you're done searching the room? So we give the robot, and this was something we've sort of argued about. Like, I'm not sure we still did it right, but we gave the robot a find action. So the robot has to decide that it's done and have found, and then pulls the string that says, I found it, and it gets a large reward for correctly finding it and a large penalty for saying I found it when I didn't find it. And so depending on the relative models of the sensor and the reward and the punishment for correctly versus incorrectly finding it, it'll decide whether it needs to look multiple times or just stop and tell you it found it. Yeah?
When you were mentioning about the POMDP algorithm, the one that you modified, the variation, you made me remember some papers in the past that they were using dynamic programming with incomplete information for doing exploration from SLAM, and it was like a similar problem. Have you seen it? You've seen something?
No, I really, 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 really want somebody to do POMDP SLAM, and maybe you guys are doing it in Nick's lab. So Nick wrote this paper ages ago about coastal navigation with Sebastian and Joel. That was kind of a step towards POMDP SLAM, but it was before POMCP and stuff, so like we have much better algorithms now. And I think that it would be very interesting to think about a POMDP. So for all this work, I assume that you've run SLAM, you have a map, you even have a semantic map, and you're just trying to find the object in the map. But I think it would be very interesting to think about how to jointly find the object and build the map at the same time, and also to try to use something like this to decide where to drive the robot when you're going out and making the map. And I think that would be really fun. It's some really beautiful math if we did it right. The term dynamic programming was invented for Markov decision processes by Bellman, because there's this really funny quote from him about how he wanted to hide the fact that he was doing math from his funders. And so he invented the term dynamic programming because dynamic can't be applied as an adjective to anything bad. It can only be applied in a way that is good. And so he invented the term dynamic programming for that reason, for value iteration and all of its friends. And then it got used in many other contexts and algorithms, but it was invented by AI people. Made me happy. Okay. Okay, so now we're going to switch gears a little bit. So we talked about uncertainty, and I wish my lab did more work in uncertainty than we do. But the other piece of language is like trying to understand language in settings where we know quite a lot about the environment. And a lot of people today, more than one person today has asked me, like, what do you think about everything that's happening now in AI and language and LLMs and stuff? So this is what I think. I think that there's two high-level approaches to language and robotics that people in the field take today. And I think it's actually a spectrum, and there's one end and the other end. We actually wrote a review paper that's under review about this, but it's not blind review, so I think I can tell you I wrote it. At one end, which is most of the work in the field, is going from English, or whatever human language, to some formal representation of what those words mean, and then somehow mediated by that formal representation, which you have to connect to the robot sensors and actuators and make the robot do something in the world. That's most of the work in the field today. The second approach, which is less of the work, just by quantity, is going from English to high-dimensional vector space to torques. Except they don't really do torques. They often do joint states or usually Cartesian end effector poses and stuff like that. And this is a smaller fraction of the work in the space. One of my favorite examples of the first kind is the SEICAN paper from Google, which, if you remember, was like making these robots understand language using an LLM. And they had these manually specified skills with preconditions. They were using the LLM to sequence the skills together. So in this view, the formal language, the formal representation, was the particular skills they chose in their preconditions. Some of the skills were learned and some of them were hand-coded, but they were all provided as input to the LLM, and I consider that a formal language. A lot of people talk about code as policies. This is something that goes from English to Python. And Turing told us that that means it can do anything. In practice, though, what it does is it goes from English to programs in a Python API that you've provided. And so what you're really doing when you're providing that API is you're defining a formal language in terms of Python and this API that you're giving it. And you're carefully thinking about what that should be, and if you do it wrong, everything isn't happy. And there's a lot of really nice reasons to think about Python, like there's GitHub and there's lots of Python code. But you are using a formal language. And the advantage of doing this kind of approach is that you can be as general as the formal language. So a lot of times, because you've got this formal thing, it's really easy to switch between different robots or different environments. And I'll talk about some of that later when we get to specific work. It's also very natural to provide safety and explainability guarantees because you have this formal thing that you think that the robot's going to do. And so there's lots of very crisp things you can say and do about it and do with it. So the other approach, where you go from English to high-dimensional vector spaces to policies, my favorite example of that is Vima from Stanford, from Fei-Fei Li's lab. And they're doing, it's actually multimodal input, so it's like English and like images like as goal states and stuff. And then they're learning to produce robot policies at the level of like end effector sequences of end effector poses. In principle, this is potentially more general. Nobody can look at GPT-4 and think that there's not a lot of potential in doing the same kind of large, deep net kind of approach. In practice today, there's a lot of questions about whether what we did for the internet, the text of the internet, is going to work on YouTube, right? It might. I'm not saying, I don't know. I was also talking about with Seiji and others about RRTs. We're all a big RRT exploring the research space. I myself am more on the formal side. But there's, I'm really glad there's people on the, I was friendly ribbing my co-authors on this review paper, the deep goo side. And when I wrote this review paper, I recruited authors. I recruited Ray Mooney, Vanya Cohen, David Watkins, who are on this side so that we could really, I was like, everything we say in this paper, we should all agree on. We should only say things that we all agree are true about all of these approaches. So one paper, and I was also talking to somebody today about old papers. Just because papers are old doesn't make them good or bad. But one particular old paper from 2001 that was really a lodestone paper. I read this when I was a postdoc in Nick's group during the reading group. Is by Andrew Ng and Michael Jordan on discriminative versus generative classifiers. And it's a comparison of logistic regression and naive Bayes. And you should read this paper if you've never read it. It's one of those beautiful papers. And what it does is makes the point that if you take a pair of classifiers, logistic regression and naive Bayes, these two classifiers are mathematically related in the sense that one is exactly the generative version of the other. They're making the same independence assumptions, but learning a different formula, essentially, with different model parameters. And one has fewer parameters, the generative one. It makes essentially stronger independence assumptions, and one has more parameters and makes fewer independence assumptions. It's less committed to the features are independent assumption than naive Bayes makes. And what they noticed is that if you have a curve, so here M is the number of the size of the training set, and the y-axis is the error. What happens is as you add more data to the training set, the error always goes down, and the solid line is the generative model. The dashed line is the discriminative model on the same data set and the same data. And what happens is the lines cross. So with less data, the generative model is doing better. It goes down faster. But then it asymptotes because the assumptions that you're making are just a little bit wrong. And so with more data, the discriminative model keeps going down and asymptotes out lower. So you have this constant pattern where you put more structure in, and with less data, it helps you, but with more data, it hurts you. And I think, and they showed that this pattern happens a lot in a bunch of different papers. So I think this exact same trade-off is happening right now in robotics, and in particular in language, and you're seeing kind of the same trade-off happening in these two kinds of approaches to language understanding for robots. So in the sort of more structured kind of generative symbolic representation, we're trying to put more structure into the problem in order to be more general in certain ways with less data. And we're paying a price because nobody knows how to have a formal language that captures all of English. Nobody knows how to do that. So we're capping out our performance because there's always going to be things people can say in their human language that we can't represent in the formal language, and we don't know how to do that. In fact, that's one of the research questions. If you're on this side, a key research question is, what is the formal language that I should be using? And we're having lots of interesting conversations with people from TLPK's group and Nick's group and Luca's group, because I think a lot of the work that you all are doing is kind of providing primitives and compositional operators in that formal language, and thinking about ways you can learn those things so that you can map more of English to things the robot can actually do. In the high-dimensional vector space, the research questions are like, well, how can I get more data and train it besides spending gazillions of dollars on GPUs? Maybe I should spend gazillions of dollars on GPUs. But also, what are the tricks? So another thing that Leslie told me years ago at the very first Coral, she gave a keynote. She said there's 6 more things like convolution that we need in order to make this all work, right? So we need 6 more tricks like convolution, like equivariance. I think Rob was here a couple weeks ago. Like diffusion models and transformers that impose structure on the network in the right way to limit the space of the things it can learn so that we're able to process the data and do something reasonable. And in language and robotics, we have not figured that out yet, right? It's still underway. It might work and it might not. And it's my bet, maybe I'm wrong, is that we're going to need some ideas from the formal side to get put into the net to make it all happen. Okay, so that was kind of this is what I think about language and robotics with deep learning. So let's talk about some research. So what my lab started thinking about from this formal language side is like, well, let's like one of our operating MOs is like, let's pick some language that we can't do, and then let's extend our formal language so that we can do it, and then let's write a paper about that. And so we've done a bunch of work with that in mind. So we did a bunch of work about hierarchical abstraction. I'll talk about this particular kind of temporal abstraction. So we noticed a lot of language that people wanted to say to robots was stuff that had temporal constraints. So here we want to say, go through the yellow room to the blue room. So if you're thinking about this as a kind of goal-based thing about where you are right now, if this is specifying a goal, it's kind of a weird goal, because if you want to, it's not just about where you are right now, right? So if I'm at the end of my trajectory and I'm in the blue room, I also want to know how I got there, to know if I followed this command correctly. I need to know if I came through the yellow room or through the green room. Here, the blocks are meant to be the colors of the room. So there's something about the past that I have to put into the model in order to treat this as like a Markov goal-based kind of way. And that made it weird, because we were trying, like we had some work where we were thinking of things, we were trying to decide if a command was goal-based or action-based. If it was action-based, then it was a constraint on the actions and you had to do it one way. And if it was goal-based, it was something that you sent to the planner and you had to do it another way. And the action-based way also felt kind of weird, because we have really good planners and we want to let them do their job and we don't want to like rewrite them. So we really liked the goal-based way. So the question was, how can we think of this as in a goal-based way, but be able to handle these kinds of constraints like go through the yellow room? So the way that we approach this is by looking at a particular kind of formal language that already existed that we didn't make, which is called linear temporal logic, or LTL. And there's been a bunch of folks for a while doing work in LTL and robotics. Hadass Kresge-Zeit kind of kicked off that whole thing. And before Hadass, there's a bunch of people in programming languages and other areas. So Hadass didn't invent LTL either. It's like a thing that people use. And what it is an extension to predicate logic that adds temporal constraints. So it adds these operators like globally P. So P has to be true at all the states. Or P has to be false at all, because you can mix in first order logic. Or P until Q. So P has to be true until Q, this other state, is true. Or finally P, at some point in the trajectory, P has to be true. At some point, I have to get to where I want to go. Or next P has to be true in the next state that I'm in. So it adds these temporal operators to logical expressions. And so we started thinking about what the cool thing about LTL is like, if you think about it from this goal-based way, you can say, well, I get my language command, I convert it into an LTL goal specification with these temporal constraints. And then what you can do is compile the LTL into a state machine and collide the state machine at high speed with the underlying MDP for the robot. And basically add those states onto the robot, underlying robot state. So the underlying robot state is kind of what I call the natural MDP for the robot, of like, where am I right now? Where's all the objects? And I'm fully observed, so we're not thinking about POMDPs, just where am I right now, okay, without the history. And when I do that, what I get is this merged MDP, this crossed MDP, that has just enough memory to evaluate this one language command that I gave. So if it was go through the yellow room to the green room, it's going to add one extra state for whether or not I've ever been in the yellow room. Yes, no, this one extra state. Instead of having to remember my whole history of everything. What that lets me do is use my essentially same old planner that can take a goal specification and run it without thinking about all these temporal things and without thinking about all of the history, and efficiently find policies that satisfy this in a goal-based way. So we did that, and one contribution of this paper was like saying that you can do that. The second contribution was training a sequence-to-sequence model. Remember sequence-to-sequence models? We used to use those all the time. That could map from English to linear temporal logic, LTL. And we collected 846 commands of English and LTL, which was at its time the largest data set of English and LTL. And it sucked. It worked. We wrote a paper about it. But it also sucked, because 846 commands is really not that many commands for people, training these sequence-to-sequence models on machine translation and looking at millions of examples of English to French translation. So then we started thinking about strange art. Thanks, guys. So there's a couple problems with this. One is that you were always finding things that people wanted to talk to you about that were not in your training set. And even with foundation models, this is probably in your training set. You can probably do this with a vision and language model. This was a piece of art that went away during COVID at Brown. And the weird thing is that it's quite large, and the lamp is interpenetrating the bear's head for some reason. It's very strange. It's also extremely distinctive. So it's the best thing to use as a landmark. If you want to meet somewhere and be absolutely unmistakable about where that is, this is the way to do it, right? And so the challenge is like, how can I have a way to take my robot to a new place where there's a big blue bear? When I was at Stata, I used to use the cow. Is there still that cow downstairs? That cow, this weird thing, like you're in a building, but there's a cow. Like that is statistically very unlikely, but therefore, because that is statistically unlikely, that's why it's a good landmark. So how can I make my robot be able to understand commands about the cow that's downstairs, or the police car with the flowers on it, or the weird tilty mirror, all of which are very distinctive, without having to collect language from that setting in that environment. So what we did, we had a couple tries at this, but one thing we did is observed that for many of these objects, it's actually there in a map. We don't even have to make it. So the big blue bear was in the OpenStreetMap model of Brown's campus. And so now the challenge is like, well, how can we leverage this information in the semantic map in order to follow natural language commands? So to do this, we had a paper that was just published at Quora last year with Ankit was here at MIT in Julie's lab. I think that's all who was here, all the authors who are here. That Ankit is Ankit Shah, the last author. I think everybody else on the paper was from my lab. Where we used a large language model to create a system where you can unbox the robot in a new environment that it's never been in before, somehow provide a semantic map of the environment. So you either ask Luca or you download the OpenStreetMap map. And without collecting any additional data in that environment, immediately begin to follow natural language commands. And large, complicated commands with lots of constraints. So like visit the front desk and then the white table. In addition, if you visit the staircase, you must avoid the elevator after that. So these are rich constraints that SayCan and its friends can't do. And it's very natural to do with the linear temporal logic. So the way that we made this work is we tried using an LLM as a black box, and it doesn't work because it doesn't know how to integrate the information into the semantic map. And so what we had to do instead is use the LLM 3 times in like 3 different ways. So first, to extract the referring expressions like big blue bear and tell us what parts of the command we had to go look in the map to find. Second, to go look in the map. So if you have a semantic map, the way we thought of the semantic map is like we know where landmarks are, and the landmark has arbitrary text descriptions saying what it is. In general, this could be vision as well. So if you had a vision language model, it would be fine to use that. But in the work we did, we used text. So it has to take the text from the command and whatever descriptions you have of the landmark and figure out what landmark you're talking about. And then finally, we used it to do symbolic translation. So once we took away the referring expression, we had sentences like go to A and then to B. And it was always A and always B. The landmarks were always like one of 5 different letters. And so then we could use the LLM again to do symbolic translation of English to LTL with these landmark parts, these open domain parts taken out, in order to go get an output formula that we could then follow. I'm running out of time, so I'm going to skip the results, but just say we were able to do 88% accurate at understanding commands on previously unseen OpenStreetMap environments. We can take the same model and run it on Cleanup World with no retraining and no new data collection, and follow commands at 80% accuracy. We tried a whole bunch of Spot. We ran something to make semantic maps on our Spot robot, and it works in that setting as well. Again, the same model with no retraining. And we made a new evaluation data set of a lot more LTL commands with more templates. So what that means is more different types of formulas. It's not just go here and then go here and then go here and then go here. It's more richer constraints. Okay, so if you're interested, I like to think about it makes language understanding more like speech recognition is, where you can, if you want to understand language, you give it the semantic map, you give it some kind of motion model, and then you can give language in and get out robot movement, which I think is pretty cool. Okay, I'm going to completely skip this paper. But the other advantage of LLMs is that you get to, of LTL in particular and other formal representations, is that you get to make safety guarantees. One thing I didn't realize until I started working at Realtime is like a cobot. I've heard the word cobot a lot, NSF uses it and stuff. It's like a specific industry term that refers to these ISO 61508 specifications. It's literally a promise if I hit you, when I hit you, because I make no promises not to hit you. I might hit you. When I hit you, I promise not to hit you too hard. That's what a cobot means. And it means that promise to 10 to the minus fifth, according to these specifications. They did a safety risk assessment, and they decided, this German insurance company called TÜV decided, and then transitively, if TÜV approves you, everybody else does too. Like, it's much easier to go everywhere else once you get through the TÜV process, TÜV. And that is how robots are used in factories today. There's somebody that did a risk assessment and made this promise. I didn't finish writing that, but they have like dual redundant joint encoders in order to measure the currents and stuff and make sure that they're not moving fast enough, that they're respecting those safety joint limits. And it really boggles the mind to imagine how a deep net would be able to make that same kind of promise that satisfies these specifications. So one of the advantages of using LTL is that you get to say, well, I have this formula and I can bless the formula somehow. Maybe I can have an expert, maybe I can go from language to LTL, and then I can have an expert bless that formula and have my safety certified to 10 to the minus fifth safety constraints. And then later, at runtime, after I've got my safety constraints specified, I can understand language with whatever way I want. And if I use LTL, I can immediately tell you the formulas are in conflict and there's a safety violation and this is why. But if I use whatever other deep net thing that I want, like something I have no insight into what it's doing or why, I can do language understanding, I can do whatever chunking I want to do and start the robot moving. My LTL formula, which is safety certified, is still watching. And so the robot's going to start executing, and as soon as a safety violation is detected, it's going to kill the e-stop, stop the robot, and you will fail, but you will not fail to danger. You will still be safe. And so we talked about a really nice way to connect those two together. You could even tell the LLM, if you're using an LLM-based approach, you can tell it the safety constraints. And the LLM will do its darned best to not violate them. And you'll get this nice performance. You'll have to e-stop fewer times, but you'll still be safe. And the LLM itself doesn't have to be safety certified. So it's like this way to have the safety constraints cooperating with the, we call it the safety chip, because it kind of plugs in with the LLM model. But I'm skipping. Maybe I'll show you the video. He did a lot of experiments on the real robot. So the idea is that there's different tasks running. Sometimes they fail in ways that aren't safe. Sometimes they stop, they're safe, but they didn't succeed in doing the task. They failed by pushing the e-stop. But our method is able to be safe and achieve high levels of task success rates by combining these two approaches with lots of robot-on-robot experiments. Okay, So we're on the top of the safety chip. All right, skipping. All right, I'm also at the AI Institute. I'm not going to talk about it. This was all work that was done and is still being done at Brown, but I'm having a lot of fun there, and we are just up the road, and I'd be happy to host folks there if you'd like to come visit, if you'd like to drive a spot, stuff like that. So I'll stop there and say thank you.
So time for questions. Oh,
Luca.
Luca.
Great talk, Stephanie. So I was still thinking about the slide with the two approaches.
Yeah.
We discussed about this morning. I think it's a beautifully clean way to put the state of the art. I was wondering, maybe another way to rephrase the choice between these two approaches is doing it symbols or not. Is there the right way to think about that? Is that really the difference between these two? First one will need symbols, whatever that means. The second one will do without.
I think the real thing is it's a spectrum. And so what I think is going to win in the end is putting some kind of notion of fuzzy symbols into the deep net so that it wants to learn or is biased towards learning skills and bundles. Like, what is a symbol? It's like a bundle of conditional independence, right? It's this place where there's this thing that's sort of, we think of it as reusable or something like that. And I think that what's probably going to win is putting the symbolic abstraction into the net in the right fuzzy way that lets it learn whatever weird things it needs to learn to actually be able to handle the examples like left and right that we were just talking about, but also exploit the conditional independence that we all feel so strongly is there when we all work on symbols and skills and have this top-down view that we really think there should be a pickup skill and an open-the-door skill that is a thing that I've learned that I then can chain together in many different ways.
Yes, I agree with you. Maybe the spectrum is between very sharp, and distinct symbols versus more fuzzier one. But another huge difference I see between these two is that the first one will allow composing symbols. So we will have a natural way to scale up to more complex problems, to larger scales.
Yeah.
In the second one, it seems that we are constrained, by the dimension of the space that we pick.
Where
is the compositionally coming from?
Certainly, the way that people are thinking. First of all, I would have said that about GPT-4 before we had GPT-4, right? I would have said they can't do compositional language, whatever. Well, they can't do it, but they can. It can do that. It can do what looks very, very much like compositional language. And so I think that it's probably wrong to say that the high-dimensional vector space approach can't do that. Probably, given enough data, I think you can't look at GPT-4 and then imagine the YouTube thing. If we actually did do it, and we trained it enough, it's probably going to do what GPT-4 is able to do. The question is, what is enough? And is there enough? And it's an open question. I don't know the answer. Are there enough GPUs in atoms in the universe? Are we hitting the steep part of the exponential or not? And I don't think anybody knows the answer. I'm really glad that we're trying that. I'm also really glad that there's some people not trying that, and we vote with our time what we think is most likely to work. And so I work more on the symbolic side, and I think you do need 6 more things like convolution in the net. And one of those 6 things has got to be compositionality. You've got to be able to have the net learn to be able to do compositional things somehow. How do we do that? I don't know.
Thanks. I have a follow-up, which is unrelated, but since I'm here, maybe a quick question.
Yeah.
So for the hierarchical abstraction,
Yeah.
you said that that's a way, to speed things up. Can you give me a sense about, how scalable are these? Through the hierarchy, can you scale up, to real time, in a very large scale? What is reasonable problem that you can solve?
I don't know. I mean, what I want to do at the Institute in this space is think about connecting learned skills with task and motion planning to get the compositional abstraction. And what I think is that you can do software engineering in order to have learned skills and learned symbols and and then make TAMP work, basically, because you have the grounded grounded predicates, right? Like things that look at the perceptual world and tell you, are you in the initiation set or not? And then more generally, parameterized grounded predicates, grounded symbols. I don't like the word symbols almost, because people think symbols are just in the symbolic space, but like what it really is like a thing that looks at the swampy, high-dimensional world and tells you where you are in the low-dimensional planning space, right? So what I want to do at the Institute is kind of plug that in so that we get skill learning with Rob, and then skill composition with TAMP, and then skill studio, which is like teaching the robot, making it really easy to teach the robot new skills with a combination of LFD and RL. That's kind of what I'm thinking. Okay, hope that helps.
Great. So we are over time, so let's thank Stephanie for the wonderful talk. And here is a gift for you,
Aw,
Stephanie.
Thank you.
The mighty chalk.
Awesome.
And the reception, so if you have more questions, please hang out with the speaker, and I hope you enjoyed the talk. I'm looking forward, for the next, talk next Friday. Have a good weekend.